We have spent the previous two chapters studying a new mathematical object called graph. We studied some properties, we learned about paths, circuits, weighted graphs. Also, we learned about a special type of graph called trees. Now in chapter 6, we are ready to apply some of those concepts into finding solutions of the application problems that we discussed at the beginning of the semester. In chapter 6, we're going to try to solve the matching problem. If you recall, an example of a matching problem is the problem of assigning airline pilots to flights. Another example is the assignment of pairs of participants at a conference to rooms so that roommates have the same smoking preference. Sometimes an optimal matching may be desired. For example, a basketball coach must assign a player to guard each player on the opposing team in such a way as to minimize the opponent's total score. Such problems will be treated in this chapter. This first section, we are going to define a new concept that's called a system of distinct representatives. And this will be used in the solution of a matching problem. Let's begin with this example. Consider the summer schedule of classes in a small college. Certain professors are available to teach each course as given in the following table. There are 6 courses and 7 professors. For example here, course number 1 have the following professors being willing to teach the course or being available to teach the course. Course number 2, professors C, D, E, and G are available to teach, and so forth. Question: no professor should teach more than one course. Can all 6 courses be taught subject to this restriction? Also, if not, what is the maximum number of courses that can be taught? We could use the same idea as we did at the beginning of the semester by assigning vertices to courses and professors. For example, if you recall the example of airline pilots, we have pilots and destinations, and we simply assign edges between vertices, between the two groups of vertices, between the first vertex on the right, on the left, and the first vertex on the right, second vertex on the left, second vertex on the right, and so on. We would make this assignment and see how many of these edges would satisfy the conditions that were given. For example, in the previous, on the table of the assignments of courses and professors, notice that these professors A, C, and F, are available to teach course number 1. So if we go back here, A, C, and F, all these 3 professors would have an edge here to vertex number 1 that represents course number 1. Then we would permutate the names of the professors until we get an assignment that will give us more edges satisfying the conditions that we wanted. However, in this section, we're not going to use this idea. We are going to try to have a different way of doing this that will be a little bit more effective and take less time. If you remember, permutating the number of pilots or number of professors here, we would need to check a huge number of permutations, and even with a fast computer, that would take several years for a small problem. Okay, now we're going to create sets of professors that are available to teach course 1, course 2, up to course number 6. So we create these sets P1 with set of professors A, C, and F. Set 2, P2, C, D, E, and G. So these correspond to professors who are available to teach each course. Now here's a definition that we're going to use in this section. It's called a tuple. A tuple, if you remember from college algebra or calculus or previous math courses that you took, you probably remember coordinates when we have x and y, right? And here we're going to extend that idea to tuples. A tuple is simply a coordinate of elements from given sets. In this case, because we have 6 sets, then we're going to have 6 coordinates. And we call that a tuple, a 6 tuple, because it has 6 coordinates. A tuple is this list. The first entry here in this list, in the tuple, is an element of P1. The second element is an element of P2, and so forth. Now there are 288 of these 6 tuples. Why is that? Well, it's simply multiplying the numbers, 3 times 4 times 2, 2, 3, and 2. That gives us a total of 288 possibilities. So we can create that number of 6 tuples in this example. To solve our problem, the original problem of assignment, we simply need to find one 6 tuple, one of those tuples that has all its entries distinct, right? So because that will represent, if all the entries are distinct, that means we don't have any repeated professors. If you remember, one of the restrictions was that a professor can only teach one class, one of those 6 classes. We cannot have a professor teaching more than one. And for that to happen, we need to have a tuple that has all entries that are distinct. And you can see how we model that problem into um, um, a problem of finding a tuple with all of its entries distinct. And that's actually how we call these tuples. A tuple that has these entries that are distinct, this is called a system of distinct representatives, an SDR for short. So in general, the definition is this. If you have sets and sets, and not necessarily distinct, some of these sets could be the same, could be equal. An SDR, or a system of distinct representatives for these sets, is simply a sequence or a tuple of distinct elements such that each element, the first element belongs to the first set, the second element belongs to the second set, and so forth. If you're able to find such a tuple that has all elements that are distinct, that's called an SDR for those sets. So let's take a look at this example. This one is on page 314 of your textbook. And here we're given 4 sets. Set 1 is 1, 2, 3. Set 2 is 1, 3. Notice that set 2 and set 3 are the same. Let's find out whether this has an SDR or not. Okay, we begin by looking at a 4 tuple. A 4 tuple is a tuple that has 4 entries. So here is the first entry, and that entry has to have an element from the first set. Well, let's just pick a number here, just pick an element. Let's say we have element number 1 here. Then in order to find an SDR, all the other elements must be different than 1. So in other words, here we couldn't have 1, therefore we need to have 3, because see, this element here has to be an element from S2. Since 1 is already here, then we cannot use it. Now if 3 is here, and then look at what happens when we try to select an element for the third entry of this tuple. There is none we can enter here, right? Because 1 has been used in the first entry, 3 has been used in the second entry. So this doesn't work. Well, let's try something else. Let's try put element number 2 here. If we put 2 here, then the second entry could have 1 or 3. So if we put 1 here, then the third element, the third entry has to have element number 3 because element number 1 has been used before here. And then finally, we can use number 4 or 5 for the fourth element. So this is an SDR for sets S1, S2, S3, and S4. Now, it's in this particular example, it's pretty easy to find all the SDRs. We can do a better analysis here instead of just uh, picking a number at random here. Let's look at what the problem is here. Look at the second and the third sets. If we use element number 1 in the second set, that means we cannot use 1 in the second element. So as you can see here, we have two possibilities. We could have 1 and 3 or 3 and 1. So let's list the possibilities. 1 and 3 and 3 and 1 for the second element and the third element. Now in those two cases, the element on the first entry has to be 2. And the reason that we can only have 2 there is because 1 and 3 would be used in the second entry and the third entry. So the only element that is left for the first entry is element number 2. And the only elements left for the fourth element would be 4 and 5. So there you have all the possibilities. You could have 2, 1, 3, 4, 2, 3, 1, 4. You could also have 2, 1, 3, 5, and 2, 1, 3, or let me write this again, 1, 3, 1, 5. And those are the SDRs are available. These are the only SDRs for S1, S2, S3, and S4. Let's take a look at another example. Here we have 4 sets, and look at set number 4 has only 1 element. That means that the fourth entry of an SDR has to be 3. And the third element of the SDR has to be 2 because 3 is in the fourth entry, 2 has to be in the third entry. That means that the first entry has to be something different than 2 and 3, which is impossible, right? This is an example where we were not able to find an SDR. No SDR is available.